Hello everyone. How are you guys doing today? Good. How was your weekend? Was it too fast? Or okay, normal? Normal? I'm always curious about this thing because for me, time always flies. I can't do a single thing, but I feel like time just flies. Like I have so many plans for weekends. Like I always like whatever I want to do over the week, I put it over the weekend. Like I'll do it over the weekend. I'll do it over the weekend. But when weekend come, I can do only one out of many things I decided to do. So I was like, was it like, is it only me all the time it happens, or for all of you guys also same thing? All the time. So I was not the only one, right? Wow, that's good to hear. At the problem, I'm too lazy. Like it takes for me to complete everything because I'm too slow. But no, it's not, right? Time is flying. Okay, so there are a few announcements. First thing is we have a homework due tonight. Homework. So if you go to the homework tab and scroll down, I posted the questions this time. So you don't have to look at the book to find the questions. I put them together. There are only 3 questions, and 2 of them are only 2 lines. So you can finish them in 2 steps. The longest one is the last one. I should have put a different one. But anyway, the 3 question has 3 types of solution. So I want you to get used to the solution process or solution step. And in your exam, I'm going to ask one of them. And most likely it will be 3 by 3. Unfortunately, I forgot to put it 3 by 3 here. So you have 2 and you have 4, but not 3. So I'm leaving the 3 by 3 for your exam, okay? I'm going to test you on that. So that's first thing. And if you want to know how to upload, all you have to do is click. Let me go to the student mode. So you go homework. And then click on the link on the title and then go to upload. And again, you're allowed to submit only one PDF file. So if you have lots of pictures, combine them into one PDF file and then upload it. It will allow you to have only one upload, not more than one. About solution, I told you that I'm going to post a solution, and I was going to, but then I noticed that I shouldn't do it now. I'm going to do it later. Okay. So I didn't post homework 1 and 2. I will post the solution. And also, if you notice, I posted the pre-lecture notes. It means I also posted both of them in PDF file and also in Word file. So I posted our lecture notes from 1.1 to 1.3. And most likely we'll be able to finish 1.3 this week. And then next week we have no class. Monday, Wednesday, both days we have the entire week. So not the entire week, as you can say. Monday, Tuesday, Wednesday, there will be no class. Not only for us, for everyone. No classes Monday, Tuesday, Wednesday. So initially, I was planning to give you our first exam on 29, which is 2 weeks from today. But then I realized, well, if I do that, that means Wednesday would be our last class to give you the materials. And by the time you come on 29, you'll forget everything because we didn't have much time to do many things. So I decided to move our exam date from 29 to October 6th. So we have, after the break next week, we have one day. I'll tell you what will be in the exam, so you can study that. Wednesday, there will be no class. And then when you come back, we are going to have the exam on 6th. Okay? So exam will be entire class time, 1 hour, 15 minutes. It will be here. And the materials we are going to decide Wednesday. Whatever we are going to finish by Wednesday, the material will be up to that. So most likely the first exam will be based on 1.1, 1.2, and 1.3. But I'd love to start 1.4. But let's see. That's my plan. Any question? Any comments? Concern? Complaint?
Well, we have a homework on like after the 29th, so we can review for test of the
Yeah, that was my initial plan, to give you a big homework set before the exam. So this week means next week, I'm going to create that and then I'll make it available. So before the exam, you can turn them in and I'll post the solution. Maisha. So 6A, 6D, and so what do you mean 6A, 6D? Like, there were 3 questions, right? Oh, yeah. So I put one question from question 5, sorry. Yeah, from question 5. So you don't have to look through the book. I posted the picture of these 3 questions on Brightspace. 5A, 5, the whole thing for question 5 or just? No, for tonight's homework, it's 6A, 6D, and then one question from 5. I forgot the number. But I have all 3 questions posted on Brightspace. So you don't have to look for them. You have the picture on there on Brightspace. Picture of the questions. So there are only 3 questions. And you'll find all 3 as a picture format on the Brightspace under the homework 3 tab.
I'm writing down the questions for you.
Brandon, question? Question? Right, that means you have to do only one more question. I forgot which one is from 5. Probably this one is from 5. I forgot which one. So this is 60. And one of them is 6A and one of them is from 5.
This is all the stuff that's due today?
Yes.
Oh, okay. So it's not next week.
But if you can do it tonight, I have the time till Wednesday midnight. If you cannot finish them by tonight, I'm putting the last due date Wednesday midnight.
Is there homework also for Wednesday? Oh, no, okay.
Any other question?
Yes. What did you mean by she's asking about question 5 is a picture?
No. So initially, remember on our last lecture, I said your homework is 6A, 6D. But then I realized I should give you 3 questions for 3 types of solution. So I put one of them from question 5. Which one I forgot? I think it's 1 or 2, one of them.
Okay, so it's no pictures, it's just equations and all.
Right, I'm talking about this picture. This is a picture.
Right, she can't,
This is an image.
it doesn't read her the picture, so that's why I'm gonna send you. I'm gonna tell you what they are. Okay.
Okay. Okay, so our first exam will not be September 29. It will be 3 weeks from today, not 2 weeks from today. Okay, 3 weeks from today on October 6th. Question.
It's a 1.3.
We are done at 1.1, 1.2. Today we are starting 1.3.
That's gonna be the exam.
Of course. So our first exam most likely will be on 1.1, 1.2, and 1.3. And I also posted these notes on Brightspace without any solution. So if you want to know the solution, you have to go to the recording. I posted all the recordings. And if you have no idea what recordings I'm talking about, if you go to Brightspace, under content, you see class recording. You can click on class recording and view the playlist. It will take you all the recordings we have. So since I'm teaching the same class twice, I have the same class twice here. Sometimes I do one question in my second class. Sometimes I do one question with you guys. So when I have many questions, but we have short time, I do half here and half on the other class. So whatever you don't see the solution in this class, Go watch the recording for my other class. You'll see the solution there.
Oh, which one is our
5.
one five?
We are 5, and then my afternoon. The later class is 6. I'm teaching the same materials, but sometimes I explain differently. Sometimes they have many questions to ask, so I explain even more details. You guys are like stage 2, so you don't have to ask any questions. But my second class, they always ask, what is this? What is that? Why is this? Why is that? Like, they ask too many questions, which is good in one way, but in other way, it takes so much time. But anyway, so I posted all the recordings here. If you want to see anything, just watch the recordings. Plus, I also mentioned the section name. So whatever section you need to fill out your solution, just go to that section and you'll see the solution.
Which section are we?
5. We are 5. We started at 5:30, so we are 5. Any other question before we start? No? Okay, so matrix arithmetic. It means we are going to add, subtract, multiply, divide matrices here. But before we start talking about matrices, first you need to know what is a matrix. A matrix is a rectangular array of numbers written within brackets, the square brackets, denoted by an uppercase letters. So, example, this is a matrix, and we name it big A. We can name it also big B. So when you name a matrix, we use uppercase letter. We do use lowercase letters, but not for the name of the matrix. We use lowercase letter for the elements of the matrix. So in a matrix, every number you see, or every variable you're going to see inside the matrix, we call them elements. For example, here, this matrix has 9 elements. Here in the B matrix, it has 4 elements. So everything you see, we call them elements. And if your matrix has m rows and n many columns, we call them, it's called an m by n matrix, but we don't write by, instead of by, we write x. So m times n, the times is actually by. So m by n matrix. M is the row, n is the column. So anytime you mention, and that m by n, we call them the size of the matrix. Or it is another name, the order. So it's the order of the matrix or the size of the matrix. If order sound harder, use size always. For example, this is a 2 by 2 matrix. The size of this matrix is 2 by 2 because it has 2 rows and 2 columns. Anytime you mention the size of a matrix, you must always mention how many rows it has. And then you mention how many columns you have. The m and n, those numbers like 3 by 2, 2 by 2, 5 by 3, those numbers are called dimension of the matrix. Number of rows are always given first, and then the number of columns. And in a matrix, if you have same number of rows and columns, like 3 columns, 3 rows, or 2 columns, 2 rows, or 5 columns, 5 rows, if the size are the same, then we call them square matrix. And you love to work with square matrix because only square matrix has to have inverse. If your matrix is not a square matrix, it cannot have an inverse. But we would like to work with the inverse because it tells us what the solution. That's why we want to work with a square matrix most of the time. And in a matrix, every row you see, they are the row vector. Every column you see, they are the column vector. So for example, in this matrix, the name of this matrix is A. We have 9 elements and the size is 3 by 3. In this 3 by 3 size, we have 3 row vectors and 3 column vectors. For example, our second row vector is -3, 7, 10. Our first row vector is the top one, our third row vector is the third one. So each row is a row vector, each column is a column vector. If your matrix has only one row or one column, there are special types of matrices. For one column, we call them column matrix. If your matrix has only one row, we call them row matrix. So if your matrix has more rows and columns, then we just call them matrix, and each row is a row vector. Each column is a column vector. However, if the size is only one row or only one column, we call them either row matrix or the column matrix. Maisha.
So all the square matrix, all the square matrices, sorry, they're all coefficient matrices, right?
Yes. Good catch. Okay. So for example, we have 2 rows, 3 columns. So this is a matrix 2 by 3. In this 2 by 3 matrix, we have column vector 1 here. So when we have column vector, we can use the lowercase letter. But you cannot use the lowercase letter to name a matrix. You can use it to name a vector, not the matrix. So column matrix, A1 means our column 1 is this, A2 means our second column is that, and A3 is our third column is that. So when you use column, you simply use lowercase letter and then a subscript to represent which column you're talking about. So we have big A, so we use small a for column, and the superscript 1 means the first, superscript 2 means the second, and 3 means the third. On the other hand, if you want to represent the row matrix, then you have to do slightly different thing. On the top of your name, you have to indicate an arrow. That arrow is telling you that you are going row-wise. So when you indicate a row vector, you have to indicate that with an arrow. But when you name a column vector, you don't have to do that.
You said before that if it's only one column, then it's a column vector,
Column matrix.
column matrix.
Mhm.
So here, it's a little confusing because you have 3 minus 1 as the first column, but then A1 is
These are-
assuming
these are-
that it's just that?
These are column vectors. Column matrix is if you matrix, the entire matrix is only one column.
Okay.
Does it matter if you use braces for the row? Just use parentheses there at the bottom.
Some people use parentheses, but I prefer brackets. And also, if you use bracket, you cannot use comma. So if you use parentheses, you have to use comma. Did you notice they have comma between each number? So if you use parentheses, you have to use comma because this is not a matrix anymore. So you have to, matrix is only represented by square bracket. Since it's not square bracket, this is not a matrix. Since it's not a matrix, so you have to use parentheses, comma, sorry.
Could we do the rows with the brackets instead?
So you definitely can write this in a bracket, but then you don't put comma anymore. So let me show you here. When you use row vector, you can write bracket 3 space 2 space 5 and then bracket. These are bracket, okay? So for bracket, no comma. If you use parentheses, you have to put comma. And you must always have to put the arrow, otherwise you will assume it's a column vector, which is wrong. Row needs to be indicated, but column doesn't need to be indicated. Column is by default, but row is not default. And in a matrix, whatever element you're talking about, we call them the position. So which position you're talking about? For example, Let's start with some simple one. We have a matrix 2 by 2, so it's a square matrix. So the first position we call them A11, means it's column 1, row 1, column 1. So the position of 1 1 is 1. 1 1 is 1. Okay, next the green one. It's in the first row but second column. So its position indicated by a, the small a, for the vector, for the row vector, and 1 means first row, 2 means second column. So if I ask you what is the position of A12, means go to the row 1, go to the column 2, what number you see there? So if you go row 1, column 2, the number you see is 2. The 3 is row 2, but column 1. So the position is A21. So it's not 21, it's 2, 1. It means row 2, column 1. So row 2, column 1 position is 3. And the last position is row 2, column 2. So this position, the purple position is A2, 2. 2 is for row, 2 is for column, it's 4. So anytime you talk about any element, you don't say, oh, the 4 there, the 4 there, the 3 there. You don't say that. You have to tell the position, which position you're talking about. When you indicate a position, first always the row comes, which row you're talking about. And then the column comes, which column you're talking about. So the row and column, you combine them together, and that's the position of an element. Okay, so don't read 11, 12, 21, 22. No, you have to read it as 1, 1 means row 1, column 1. 1, 2 means row 1, column 2. 2, 1 means row 2, column 1. And 2, 2 means row 2, column 2. So it's not 21, 22. It's 2, 2, 2, 1. Maisha.
So how do you know, like, if you're gonna make it, how do you know if it's supposed to be like, if those are the coefficients or if those are just like the directions?
All of these metrics, they're coefficient metrics. We use augmented matrix when you solve a matrix.
No, but like 1, 1, 1, 2, right?
That's the position.
So how do you know, when you look at a matrix, how do you know if they're telling you the position or if those are the actual coefficients?
Those 1, 2 are subscripts.
Oh, okay.
Okay, so you write small a, and then on the next to small as a subscript, you indicate the position. 1, 2, 1, 1, or 2, 1, 2, 2. And then equal, and then whatever number you have at that position. And then in a square matrix, we have diagonal. Those diagonals, we call them principal diagonal, means they're the main diagonal. And the position for all the principal diagonals are double-digit same number. For example, in this one, we have diagonal 1 and 4. The position for 1 is A11, means first row, first column. The position for the second diagonal, second element of the diagonal is 2, 2, means 2 row, column, row 2, column 2. So all the diagonals, the principal diagonal, their positions are 1, 1, 2, 2, 3, 3, or 4. Any questions so far? Okay, so now we know how to read a matrix. So we are going to the properties. What type of properties they have? First one, two matrices have the same size if and only if they have the same dimension. So if you are given two matrices and they ask you whether this matrix are the same size or not, whether they have same size or not, all you have to do is look at their dimension. And dimension means how many rows and how many columns they have. So two matrices are same if they have same number of rows and same number of columns. So the size of two matrices are same if they have same number of rows and same number of columns. On the other hand, two matrices are equal only if every element in both matrices are the same element. So many matrices have same size. They may have same size, but not they're equal. Two matrices are equal if they are same matrix. So if you have 1, 2, 3, 4, that means the other one has to be 1, 2, 3, 4. It cannot have any element different. In order to be the same matrix, you have to have the same thing repeated twice. And then this addition. Two matrices of the same size may be added by adding corresponding entries of the matrices. In other words, if you want to add or subtract two matrices, the requirement is they have to have same size. Means they have to have same number of rows and same number of columns. If they don't have same number of rows and same number of columns, you cannot add or subtract them. And when they have same number of rows and same number of columns, then you can add them by adding their corresponding positions. For example, here, I have two matrices A and B. A matrix has row-wise 1, 2, 3, and then second row is 4, 5, 6. B matrix, row-wise 7, 8, 9, and then second row is 10, 11, 12. So 1, 2, 3, 4, 5, 6. And you're adding 7, 8, 9, 10, 11, 12. We can add them because both A and B, they have 2 rows, 3 columns. So we can add them. And when we add them, we are going to add their corresponding positions. So let me do A, and you can try doing B. We are adding A and B. So when we add, we take the first position of A and first position of B. First position of A and first position of B. Let me take something out. So A. We are adding A plus B. So we have 1 plus 7 in 1, 1 position. Then in 1, 2 position, we have 2 plus 8. So we have 2 in the second row, in the second column in the first row, and 8 in the second column in the first row. So you add the corresponding position, the elements you have on the corresponding position. And then lastly, we have the third column first row. So you add both elements on the third column first row. So 3 plus 9. So that's the sum of A and B. And then you go row wise, the second row. You have 4 and 10 on second row, first column, so position 2, 1. You add them, 4 plus 10. And then you have 5 and 11 on the second position, second column, second row. It's 5 plus 11. And then the last position in both matrices, we have 6 and 12. So you add 6 plus 12. So you go position wise. You cannot change their position. You cannot switch their position. You have to add the exact position. Whatever elements you have on the exact position, you have to add them together. Obviously, we're going to do that mentally later on, but now I'm showing you for the first time, so I'm doing the details. So we have 8, 14 column wise on the first column. Then we have 10, 16 column wise in the second column. Then we have 12, 18 column wise on the third column. And that's our resulting matrix when we add A plus B. That's the sum matrix.
What allows you to add two matrices at the same size? Isn't it possible that like x1 for matrix A and x1 for matrix B could be different values?
They can have different values. The thing is, as long as they have same size, you can add the same position.
So would it become like a new, like
It
x1
becomes a
value?
new. So basically, you are adding two and then getting new one. So you're shifting your original one a little bit further from the original ones. So if you think of it as a point, you're adding 2 points. It will also be somewhere different, another point. Now you try the second one. Subtract A from B.
Is this new matrix called C?
Yes. This is what they are indicated here. The C matrix is A plus B. Now your goal is to find another matrix D, which would be B minus A. So go ahead, try that. Find your D matrix by subtracting A from B. Oh, I forgot to take attendance. Let me take that attendance now. Today is 9:15. Brandon C. Joseph. Justin. Zibran. Shivu. Michelle. Jack. Ashif. Darius.
Here.
Winston. Abigail. Shane.
Here.
Emily. Kanar. Christine. Edison. Maisha is here. Brandon. Alvin.
Here.
Shafal. Alexander. Shitila. Wenchuan. Wenchuan. Hailun. Okay, are you guys done? Hailun, can you help me with this, please?
6.
B.
Oh.
B minus A.
The answer? 6.
Oh, you're telling me 6. Oh, okay. 6.
6.
Are you going row wise or column wise?
Column 1.
Okay, so 6, 6,
6.
6,
6.
6,
6.
6.
6.
All of them are 6? Okay. Is it correct? Good. So when you subtract, you take the first position of B matrix, subtract the first position of the A matrix. So we have 7 minus 1, 6 on the first position, A 1, 1. Or we should say D 1, 1 because this is D matrix. Then the second position, so A, you take B 1, 2, and you subtract A 1, 2. So 8 minus 2 is 6. And you go similar. Any question? Comments, concern? No? That's how we add and subtract. And then we have a zero matrix. Zero matrix is all the elements we have in the zero matrix is 0. They have no other number besides 0. It's 0. So they are saying if you add zero matrix to any matrix, it doesn't change anything. For example, you may have an A matrix 1, 2, 3, 4. And you have a zero matrix, let's say Z, 0, 0, 0, 0. In order to add or subtract with A, you have to have the same size. So my A is, what is my size of A? What's the size of A matrix?
2 by 2.
2 by 2. That means your zero matrix has to be 2 by 2. Whatever you want to add or subtract, they have to have the same size. So if you add A and Z, it means you're adding 1 plus 0, 2 plus 0, 3 plus 0, 4 plus 0. So the sum A plus Z is 1, 2, 3, 4, which is the same matrix as A. So adding or subtracting a zero matrix doesn't change anything. Maisha.
Sorry. So, like, when you, like in the last lesson, we were trying to do, reduce row echelon.
Mm-hmm.
So I know you can't, like, multiply
By a
rows
zero.
by zero. So can you just,
But we can add a zero when you're not solving. When we use reduced to echelon when you're trying to solve a matrix. Here we're not trying to solve any matrix. We're trying to combine two matrices.
so, when you do the reduced row echelon, can you just multiply by zero?
We cannot. No. It cannot multiply by a zero or a zero matrix. You can add if it's helpful for you. You can subtract, but you cannot multiply. That's against the rule. So we know how to add, subtract, we know how to add a zero matrix, and now we want to know how to multiply by a scalar. Multiply by a scalar is totally different than multiplying two matrices. Multiply by scalar means you're multiplying each element by that scalar. Okay? So for Maisha's sake, let me do one easy. Let's say you have a B matrix 1, 2, 3, 4, column wise, so the row wise. On the row we have 1, 2, first row, second row we have 3, 4. Now we want to find 2B. It means multiply your matrix B by 2. So what you're going to do is you're going to multiply every element in your B matrix by 2. So our first row is 1, 2. When you multiply the entire thing by 2, it will become 2, 4, row-wise. And then when you go to the second row, our second row is 3, 4. So you're multiplying by 2, means you're multiplying 3 by 2, you get 6. You multiply 4 by 2, you get 8. So if your matrix is 1, 2, 3, 4, row-wise, then twice that matrix is 2, 4, 6, 8, row-wise. Now,
Sorry, isn't it the same as multiplying by a row by a constant?
Exactly. That's the allowed condition. So you can multiply by non-zero number, non-zero scalar. Now, can you guys try doing the example here? You have a 3 by 3 matrix. Compute negative 1/2 of that matrix. So you're multiplying that matrix by negative 1/2. So let me give the matrix row-wise 1, 6, 8. Second row is 2, negative 14, 12. Third row is negative 4, negative 10, negative 14. You are trying to multiply this matrix by negative 1/2. Ready? Okay, so negative 1/2 A. Who would like to give me the answer for that? Volunteer? Shibu. Shibu, right?
Sure.
Shibu. I'll get used to it.
So I'll go by row.
Mhm.
Negative 1/2,
Negative 1/2,
negative 3,
negative 3,
negative 4,
negative 4,
and then negative 1,
negative 1,
7,
7,
negative 6,
negative 6,
and then 2, 5, 7.
2, 5, 7. Perfect. So you multiply each element by the scalar, and that's it. Question? Any question? Okay. Now we are verifying the information. I have 3 of them, but I'm not going to do all 3. I'm going to do only 1 of them. So here it says, just like we work with normal numbers, we can work with the matrices also in many cases. For example, the first one says 3 times matrix A plus matrix B is same as 3 times matrix A plus 3 times matrix B. So the number 3, the scalar is commutable. You can distribute the scalar to matrix. And if you have 5 times matrix A, this is same as 2 times matrix A plus 3 times matrix A. And if you have 6 times matrix A, this is same as 3 times twice matrix A. So you can just distribute the numbers. You can break down your numbers. You can do everything just like numbers. So matrix addition, subtraction, multiplication, they're just like normal addition, subtraction, multiplication. The only thing we cannot do is division. Metric division doesn't exist. So which one you want me to show you? Any preference, ABC?
B looks weird to me.
B? Okay. So it says you have 5A. So we're doing B, 5A. It means take your matrix A, multiply by 5. So if you multiply this entire matrix by 5, who can tell me the answer? What do you get? 5 times matrix A?
5, 10, 15, 20, 30.
5, 10, 15 row-wise. And then we have 20, 25, 30 row-wise. So this is 5 times matrix A. Now, the property says if you multiply matrix by 5, this is same as you're multiplying this matrix by 3 plus you're multiplying this matrix by 2. So that means we have to know what is 3A and what is 2A. So we are going to do 3A plus 2A. But before that, let me do 3A. Single 3A. Who would like to give me 3A? Maisha.
3, 6, 9,
Cool. 3, 6, 9 row-wise.
12, 15, 18.
12, 15, 18. Wonderful. You got it perfectly. And now we need to know what is 2A. Because we are going to add 3A with 2A. Go ahead, Maisha. 2, 4, 6, 8, 10, 12. So we are verifying here, is this true? That if we add this true, we'll get 5A back. So now let's add 3A and 2B. So 3A plus 2B. If you add, what do you get? Volunteer. Shane, right? Go ahead, Shane. 5, 10, 15, 20, 25, 30. Excellent. So if you add 3 and 2, you get 5. If you add 12 and 8, you get 20. And then you keep doing it. So add first row with the first row, add second row with the second row. And if you observe, this thing and 5A have the exact same two matrices. So we can divide the matrix into 2 pieces. Not divide a matrix by a matrix. We can divide one matrix into 2 pieces. That's possible. We can multiply a matrix. we can multiply by a number, we can multiply twice, and I get the same thing back. So let me take this out. And now we are going to do matrix multiplication. So all this multiplication we did, they were not matrix multiplication, they were scalar multiplication. We multiply a matrix by a scalar. And now the real multiplication comes. How do you multiply matrix by a matrix? So here it says why to use matrix multiplication. Well, we use matrix multiplication in many places in our life. For example, if you have a business, in business applications, matrix is important because an inventory matrix, when multiplied by cost per item matrix, you get the total matrix. So instead of having a bunch of equations to work with, you can simply put them as a matrix form and then multiply, you get your cost matrix. Or if you have sports, you can figure out total cost for the equipment. Basically, they are saying cost matrix. So these two examples are from some book, but both are talking about cost. Besides cost, there are many other places we use matrix. One big field is linear algebra. When you work with computers, you have to work with, when you do coding, those stuff. We use them a lot. So the fun part. When we can multiply two matrices, just like, to add or subtract, you have a condition. Same thing if you want to multiply, they have a condition. Now for addition subtraction, our condition was same size. But for multiplication, you cannot just have same size. There is one very important requirement. And that requirement is that number of rows on the first matrix have to be the same as number of columns on the second matrix you're trying to multiply. So if you multiply matrix A and B, the number of rows in A has to be same number on the B matrix. Number of columns. So row and column, they have to match. If they don't match, you cannot multiply them. And if you can multiply them, the fun part is that the resulting matrix, the product matrix, will have the size column by row. Let me give you one example. We have A matrix row-wise 1, 2, 3, 4, 5, 6. Column matrix row-wise -2, -1, 0, 6, 3, -8. So before you go for multiplication, first you have to write down their size. What's the size of A matrix? 2 by 3. So let's write it down. We have a matrix 2 by 3. And the by we replace by a x. So it's 2 times 3, but we don't write 2 times 3. We read as 2 by 3. What's the size of the B matrix? Maisha? 2 by 2. 3 by 2. Because I have 3 rows. So 3 rows, 2 columns. So it's 3 by 2. Sorry, my bad. I should have column versus row. So if you want to multiply A and B, the position you have to check is column and row. If the column of the first matrix, the size of the column of the first matrix is the same size of the row of the second matrix, then you can multiply them. So as long as you have the same same numbers together. So the number here and the number there, if they are the same number, then you can multiply them.
So if you have like 15 by 3 and 15 by 1.
You cannot multiply.
I'm sorry, 15 by 3 and 3 by 1.
You can multiply because the 3 and 3, they're the same number. So the number of columns on the left matrix has to be same of number of rows on the second matrix. So column and row, CR. You have to have CR.
But it can't be row and column.
No. The row and column becomes the resulting matrix. So once you can multiply them, then what will be the dimension of the product? It's the row and the column. So the resulting matrix will have the other two numbers. That's the result. The condition is the top one. Row, column, and row, CR. The condition is CR. Once you have the condition fulfilled, the resulting matrix will have RC, row and column. So here it says, can we find AB? Means can you multiply A with the B? What's the answer? For this example, can you multiply A and B? Yes. And then it says, if it can multiply A and B, what will be the dimension of the product AB? So the resulting matrix will have what size? 2 by 2. Because we have 2 rows in A and 2 columns in B. So the resulting matrix will be 2 by 2. So again, in order to multiply, the requirement is CR, means column of the left matrix has to be the same number of the row of the second matrix. So row, column, and row, CR. If you have CR, then your result will be RC. CR, your condition. See, condition start with C, so you have to have C first. Condition is CR. The result, the result start with R, so the result will have RC, means number of rows by number of column. Yeah, good remember. Condition is CR, result is RC. Oh, I never thought about it. I just invented that. Wonderful. Okay.
So, for example, if this was A is 3 by 2 and B is 2 by 3, then we just like
So A is, what did you say? 3 by 2?
3 by 2.
And B is
2 by 3.
2 by 3.
So this one.
Then can you find AB? Means can you multiply A with B? Of course you cannot, because A and B, sorry, it's a 3 by 2 and 2 by 3. So yes, AB is possible because you have the condition satisfied. CR, number of column and number of row matched. So possible, yes. However, if I ask you, can you find BA? It's also possible, right? BA, we have B size 2 by 3 and A has size 3 by 2. We have CR same, so it's possible.
And then AB would be a 3 by 3 matrix.
Exactly. So for AB, the result is 3, 3. So 3 by 3. But for BA, it's not the same. It's 2 by 2. So the result is 2 by 2. And I didn't mention it here, but later I'm going to tell you that matrix multiplication is not commutative. So for numbers, we know 2 times 3 is same as 3 times 2, right? They both are 6. But for matrix, it's not true. A times B are not same as B times A. So the product of AB will be different than the product of BA. The addition is same. A plus B is same as B plus A. But A times B is not same as B times A. Okay, I have one example. Our A matrix, row-wise, is 1, 2, 3, 4, 5, 6. B matrix is column-wise. It's a column matrix, -1, 6, 0. Can you multiply A with B? So let's write down the size for each matrix. What's the size of A? 2 by 3. Maisha, do you remember what's the size of B? Good job. 3 by 1. It's a column vector. It has 3 rows, but only 1 column. Now, can you multiply the 2 matrices? Yes, because we have conditions satisfied. C, R. As long as the C for the first matrix is same as R for the second matrix, you can multiply. So yes, multiplication is possible because of CR. And why? It's because of what I said. CR. The number of columns in the left matrix is same as number of rows in the second matrix. Can you tell me the size? What will be the size of the resulting matrix, Abby?
2 by 1.
2 by 1. Perfect. Our result will have size 2 by 1, which is whatever we did not use. So that's the cool thing about matrices. They look at the condition. As long as the condition is satisfied, they will tell you what will be the size for the result. Any questions so far? Okay, let's do some example. For the following, determine whether the matrix multiplication is possible or not. And then also tell me the size of the resulting matrix if it's possible. Okay. So, do you want to volunteer or do you want me to call you guys? Volunteer? The first matrix, let me read it out loud. Row-wise is 3, 5, 1. Second row is negative 2, 0, 2. The second matrix is row, let me read column-wise. Column-wise, 2, 1, 4 and 1, 3, 2.
1, 3, 1.
1, 3, 1, sorry. So can you multiply these two matrices? So tell me the size for the first one. Brendan. 2 by 3. And the size for the second one? 3 by 2. So we satisfy the condition CR, that means yes. And if you can multiply, tell me the result. Result. What would be the size of the resulting matrix? Maisha? 2 by 2. Perfect. So if you can multiply, you need to know the size. If you cannot multiply, ignore the size. Cannot even multiply. Okay, volunteer for B. Row-wise, we have 4, negative 2, 6, negative 4, 8, negative 6. The second matrix, row-wise, 1, 2, 3. Can you multiply these two matrices? Maisha. The first row, the first matrix, it has 3 rows, 2 columns. What's the size? 3 by 2. Do you remember the size for the second matrix? 1 by 3. It's 1 row, 3 columns. So 1 by 3. The two number, the row and column, the column and row doesn't match, so you cannot multiply. So the answer is no. The condition is CR, means column and row. Column and row doesn't work, cannot multiply. Third one, C. We have row-wise 3, 2, 1, 1, 4, 5. Second matrix, column-wise 1, 4, 3, 0, 1, 4, 0, 0, 2. Can we multiply these two matrices? Shitila, tell me the size for the first matrix. Perfect, 3 by 2. What's the size of the second matrix? 3 by 3. Can you multiply these two matrices? Good job. We cannot because of the column and row did not work. So no. Last one. Column wise, 2, -1, 3. And row wise, 3, 2, 4, 5. Three by 1 and 1 by 4. So can you multiply? Yes, because we have row, column, and row same. So what would be the result? 3 by 4. Perfect.
I have a question. So you're not allowed to just swap.
We cannot,
Is there a reason?
because they're not commutative. Commutative, right? The word commutative. Like A times B and not B times A. So if they ask you to find A times B, you have to find A times B. You cannot find B times A, tell them it's A times B. More. The idea, right? So let me skip this. Now we are going to do the real multiplication. So now you know when you can multiply and when you cannot. When you can multiply, how do you multiply? So when you multiply, the multiplication is kind of fun. You know, see when you added, we added only the position, but when you multiply, we don't multiply the position. We take the entire row and entire column, we multiply their position and then add them together. So for example, we have a row matrix 1, 3, 5 and a column matrix 2, 4, 6. So what's the size we have? We have row matrix 1, 3, 5. What's the size of the row matrix? 1 by 3. And what's the size of the column matrix, Maisha? 3 by 1. So can you multiply this row with this column? Yes, because we have the same column, CR. So what would be the resulting matrix, the size of the resulting matrix? 1 by 1. Our result will have 1 by 1. Uh-oh, what is 1 by 1? What type of matrix is 1 by 1? It's only one number inside the bracket. There's only one number matrix. So let's see, how do you find it? Let me have space now. So when you find, you take the entire row and you multiply the entire column. So one row and one column. When you multiply them, you take their corresponding position and multiply. So row 1, column 1, multiply with row 1, column 1 on the second matrix. So 1 times 2. So you write 1 times 2. And then you add the next position. So plus, you take the second element in your row. So second element in the row is 3. Second element in the column is 4. So you multiply 3 times 4. What do you get? 12. And then you add the third position. So we have 5 on the third position in the row, and we have 6 in the third position of the column. So you're going to multiply 5 and 6. What do you get? 30. And that's your result. Let me make it smaller so I can fit everything together. So 2 plus 12 plus 30. And when you add all of these, what do you get? How much? 44. So that's your result. 44, it's 1 by 1 matrix. My size looks like 2. It's 1 by 1. So it's just a number in a matrix. So it's the number matrix. It's neither row, neither column, it's just a number. Any question? So we are going to do the same thing many times depending on how many rows and how many columns we have. So when you multiply 2 by 2 matrix, whatever you're going to multiply the first row, first column, that will be first position, row 1, column 1. Then you multiply the first row, second column. So let me give let's do one example and explain. We have 2 matrices, A and B. And let me take something simpler, okay, for my sake. Let's say I have A is 1, 2, 3, 4. And our B matrix is 4, 5, 6, 7. Now let me say CD, so you don't get confused. So let's say C is this, D is that, and our goal is to find CD. So C matrix is 1, 2, 3, 4 row wise. D matrix is 5, 6, 7, 8. Let me change the color. Oh no, let me change the numbers. 5, 6, 7, 8. We are going to multiply these two. What will be the resulting position? The position of the resulting matrix. Go ahead, Maisha. No, as a position means what by what? Not really. We have row wise 1, 2, and then row wise 3, 4. So they're both 2 by 2. So we have 2 by 2, 2 by 2. So our result will have, what's the size? 2 by 2. Because result is number of rows and number of columns. So number of rows in the first matrix is 2. Number of columns on the second matrix is 2. So it will be 2 by 2. We do row by row, row by column. So you take the first row 1, 2, and you multiply 5, 7, the first column on D. So first row on C times first column on D. So row and column you multiply, it goes to the first position of your result. So you have 1 times 5 plus 2 times 7 on the first position. So row 1, column 1, so position is 1, 1. So in the 1, 1 position, we write them. Then we go row 1, column 2. So row 1, column 2 is 1, 2 position. 1, 2 position. Let me change the color to something different, yellow. You take the row 1 and you multiply the column 2. So row 1, column 2 is a yellow position. We have 1 times 6, and we are adding 2 times 8. So 1 times 6, 2 times 8, and then you add them. So you take row from the left and column from the right, always. So you're done with first row of the column. Our result is the result of the first row of the results, because we have row here. Then you go to the second row and you're going to write the result on the second row of the resulting matrix. So our second row, let me put green, has 3, 4 in C. We are going to multiply 5, 7 on D. And our position will go row 2, column 1. So 2, 1 position. Row 2, column 1. So in row 2, we have 3, 4. On column, we have 5, 7. So you multiply 3, 5, 3 times 5, and you add 4 times 7. You have to take the entire row of the first matrix and go every column on the second matrix. The first row on the left matrix and every column on the right matrix. As you go every column, you're filling out each column on the first row on the resulting matrix. You multiply elements and you add the result. So the first position on the left matrix and the first position on the column matrix, you multiply them and you add the second position of the left matrix and second position on the right matrix. Second position and the column on the right matrix. So you go row on the left, but column on the right. You multiply the position and then add all the positions. So last one, give me 2 more minutes, 2 more minutes. We have our second row from the left and second column on the right. So that's our last position. Second row is 3, 4. Second column is 6, 8. So 3 times 6, the first position, and you add the product of the second position. Second position is 3 and 8, so you multiply them. 3 times 8. So that's how you add them, but obviously we're going to add them mentally later on. So the resulting matrix, you can just write in one way, in one sentence. It will be 14 and 5, so 19. And then 15, this is times 15 and 28, 43. And then we have 6 and 16, 22, right? 6 and 16. And then we have 18 and 24. Oh, sorry, it's 4. It's 4 times 8, my bad. So 3 times 6, 18, 4 times 8, 32. 18 plus 32, 50. That is our resulting matrix. And as you see, it's 2 by 2. So first row, first column goes to the first position in the row, in the result. First row, second column goes to the second position in the first row in the results. First row, third column goes to the third position in the row in the result. Once you are done with every column in the second row with the every column in the second matrix with the first row, then you go to the next row and do the same thing again. And then you go to the third row and do all the columns again. And then you put them on a matrix form. And that's all for today. In our next class, Wednesday, we are going to do 3 by 3 matrix multiplication. And Wednesday, I'm going to tell you what will be homework for this week. So have a good day. I can say have a good evening. Have a good evening. If you have any question, let me know. And,
So like I get stuck. I always get stuck. And I don't even know if I was supposed to do this.
okay.
I could do that though, right? That's allowed. Okay.
So first you wrote this, good.
Because the guy, like the guy I had in summer told me to go this way,
Yeah.
but you told me to go down. Like
or row wise, but row wise you will not always get everything 0 besides the first.
Yeah, I know, and I think that's why I keep getting messed up. I keep jumping around, and I don't think I'm supposed to be jumping around, right? Like I'm supposed to, like there's an order I'm supposed to go.
Jump around, but it will take time.
Yeah. Like that's not.
If you want to save your time, you have to go column wise. Row wise is possible. It's not against the rule. It's possible, but it takes time.
So should I try to make this 0 before I touch this one?
Before you touch the first row, first your goal is to make this -1 into +1, which you did perfect.
Oh,
then,
I should do the pivots first,
Mhm.
and then go back to the numbers.
So first you want to have each leading coefficient, and below them you want to add 0.
Mhm.
Once you have that fulfilled, then go ahead and get rid of everything else if possible.
Okay, so just worry about first, like, so pivot, clear that column, pivot, clear the column, pivot, clear the column.
So here you have -1, you made it to +1
Yeah,
grid,
the pivot.
and now your goal is to get 0 below 1.
So I could do, I could do either 3R1 or
But this is
2.
better because you want to get 0.
Yeah, so I gotta do like 3R1 minus row 3
Plus.
or plus row 3. Yeah, okay.
So you get 0, but these will not be 0
Yeah, those are
anymore.
gonna change then.
It doesn't matter because your goal is to get,
Oh, I just gotta keep pushing this guy over too. Yeah.
you
Okay.
want 1 0 0, and then whatever you have, the second row is the 1 0, and then the last one you want 1 here.
Okay.
That's your goal.
All right. I got you. All right. Thank you, miss. It's just this, right? For the homework. Like,
Sure, no problem.